Imagine a user on an offline-first learning platform. They are endlessly scrolling, swiping through heavy, high-definition video modules one after another. Behind the scenes, the application is performing a seemingly harmless task. It is naively saving every single opened file directly into the local memory of the user's device. Eventually, it hits a breaking point. The device's RAM meter completely maxes out. The operating system throws an out-of-memory error, and the application instantly dies. If a system handling continuous data lacks a self-cleaning eviction policy, it will eventually crush under its own weight. Unchecked memory allocation is a fatal architectural flaw. The necessary fix here is a strict cache limit, a fixed capacity where the system automatically deletes the oldest, least relevant data the moment it gets full. But there is a severe performance constraint. This process of evicting old data and inserting new data must happen in O(1) constant time. That means the operation has to take the exact same microsecond, regardless of whether the cache is holding 10 items or 10,000. Standard arrays fail this test immediately. If you delete the oldest item at the front of an array, you have to physically shift every remaining item down a slot to maintain chronological order. That requires O(n) linear time, causing unacceptable lag as the dataset grows. As this comparison shows, hash maps also fail, but for the opposite reason. A hash map provides instant O(1) lookups, but it drops the data into a randomized, chaotic cloud. It possesses no internal chronological order, leaving the system with no way to determine which item is actually the oldest. We are left with an engineering paradox. Building a viable cache requires synthesizing the instant speed of a hash map with the strict chronological order of a sequential list. Look at this structural synthesis. To solve the paradox, we take a hash map for instant lookup and couple it directly to a doubly linked list, which acts as a chronological conveyor belt. The layout of this conveyor belt is strictly ordered. The head of the list holds the absolute newest data, while the tail represents the oldest. This list must be doubly linked. Every node carries both a previous and a next pointer. If a piece of data is ripped out of the middle, the surrounding nodes use these dual pointers to instantly bridge the gap without requiring a system-wide shuffle. We also install dummy head and tail sentinel nodes at the extreme ends of the list. These are empty permanent bookends. Because they never move and never hold real data, the system can perform constant data surgery between them without ever triggering a crash-inducing null pointer error. This hybrid architecture gives the system the power to instantly locate any file and rewire its physical timeline without ever having to search the list. Let's see what happens when new data arrives, but the cache has hit its absolute capacity limit. The system must trigger a put eviction. The exact target for eviction is always known. We go to the node sitting immediately in front of the dummy tail. By definition, this is the least recently used item. This requires a dual deletion. The targeted node is severed from the linked list, and simultaneously its corresponding key is completely erased from the hash map. To complete the put operation, the newly arrived data node is inserted directly behind the dummy head, officially claiming the title of most recently used. Deletion at the tail, insertion at the head. This synchronized dance allows the cache to maintain a strict size limit in flawless O(1) time. There is a misconception here that trips up a lot of developers. It is the assumption that an LRU cache only updates its internal order when brand new data is written to it. Think about the offline learning app. If a user rewatches an old video module, but its position on the timeline isn't updated, the cache will incorrectly flag that active video as obsolete and incinerate it. The absolute rule of the LRU cache is that simply accessing or reading existing data must trigger a timeline update. Watch the mechanics of the get operation. The hash map instantly finds the requested node, severs it from its current position in the middle of the list, and yanks it all the way to the front, locking it in directly behind the dummy head. Within this architecture, there are no passive actions. Reading is treated with the exact same structural urgency as writing. This flawless speed carries a hidden tax. We have to look at the system's space complexity. This diagram illustrates the memory footprint. To manage this system, we are storing two distinct data structures, the hash map and the doubly linked list, to track the exact same set of items. This effectively doubles our structural overhead. Formally, this is defined as O of capacity space complexity. The memory required scales linearly with the maximum number of items the cache is allowed to hold. You can achieve absolute speed, but you must pay for it with absolute space. Let's return to the offline learning app, retrofitted with this bulletproof LRU cache, where older data packets are seamlessly dropping away. As the user scrolls infinitely, the RAM meter holds steady, preventing the memory exhaustion that would previously have killed the process. This specific combination of data structures extends far beyond mobile apps. It is the exact foundational engine powering massive systems like Redis, MySQL buffer pools, and operating system page replacements worldwide. The LRU cache is the silent, self-cleaning mechanism that prevents our systems from seizing up under the weight of unbounded data.